Hi there. My name is Mark Reinhold. I work on Java, and this is a talk about the modular Java platform and project Jigsaw. But first, a word from our sponsor. We have the first JDK 8 release candidate as of a couple of hours ago. Don't download it now. Matthias will kill me. But jdk8.java.net, when you get a chance to get better connectivity, please download that, do any final testing, and if you find a showstopper, please tell us. Anyway, that's not what I'm here to talk about. So what I am here to talk about is modularity. So why are we working on this? Three major reasons. One is to scale the Java platform down to small devices. The second is to improve application performance. Excuse me. And the third is to improve platform security and also maintainability along the way. So in terms of scalability, getting Java to run on a small device when you want something more than Java ME, which of course is really small, it's kind of a problem. These small embedded computers have gotten pretty powerful. Their processors can run an SE class virtual machine. The problem is their storage is still quite limited. It's limited in bandwidth and it's limited in size. Now, usually these days we think, memory is pretty cheap, right? But if you're going to stamp out 500,000 embedded devices, then another 50 cents or a dollar or a euro or whatever for an extra 50 megs of memory can add up in that kind of quantity. The difficulty is Java SE has always been designed and specified as this monolithic thing, and implementations of it have always been done as these big monolithic things. So right now, if you look at JDK 8, the smallest build that we have configured for an ARM32 processor is still pretty big. It's just not working. It clocks in at 54 megabytes. And it's not a very satisfactory answer to say, oh, dear Mr. Embedded Developer, you've got an application and it only uses this API and that other API, but you need to budget an extra 54 megabytes because you need to carry the rest of this platform around, even though most of it will be unused. So as a step toward addressing that problem, and this is part of the general trend of trying to converge the Java ME and SE platforms, we've defined a set of compact profiles in Java 8, a series of layers, kind of like an onion. So the very smallest profile, complete technology failure here. Very smallest profile, called Compact 1, is about 11 megabytes. It's got the bare minimum in it, so Java Lang, Java Net, Java IO, Java Util, NIO, basic security APIs, but not really a lot else. Compact 2 adds a few things. It's got JDBC and RMI and JAX-P, so you can do basic XML processing, but not fancy binding or web services or any of that stuff. Compact 2 is 16 megs. Compact 3 adds yet more things. You get instrumentation and authentication and naming and row sets and the compiler API and XML digital signatures, although I still haven't met anybody who actually uses that. And then finally, the rest is in the full JRE. So that includes FX and crypto and SCTP and JAX Web Services and the HTTP server and the Nashorn JavaScript engine. So this is good, right? This is an improvement. If you're writing an embedded app that only needs to use RMI and JAX-P, then you win. You only need to dedicate 16 megs to this compact JRE. The trouble is the amount of flexibility here is kind of limited. If you write an application that needs, say, Java FX and Nashorn and RMI, well, even though you're not going to use the rest of the stuff in the full JRE like Corba, you have to pay 54 megabytes to carry the whole thing around. It's indivisible. So To address this problem, let's do a real job of modularization. Now, of course, the history here is we wanted to do a real job of modularizing the platform in 8, but due to various circumstances, such as a large swath of security vulnerabilities, we were unable to get that done in time. So compact profiles are a down payment on getting that done, hopefully the right way, in 9. So how do we go from these profiles to modules? Well, let's cut things up into a finer grain and look at the other modules that comprise the system. So the base module, the one in bold at the bottom, that's the very smallest one. So it's got Java-lang object and Java-lang string and all the other stuff that you really can't do without. Other things that are in Compact 1 that correspond to modules are TLS, the SSL APIs, logging, and scripting. Other things to add in, filled in a few things: management, Kerberos, cause naming, and then the ones that are above the JRE, way up there, tools and dev tools and tools.base and so forth. Those are the modules that make the JDK above the JRE. Remember, the JDK includes the developer tools on top of the JRE. Now, when you've divided the platform into modules, one of the problems is that the relationships between the modules are much more complicated than the relationships we had between the layers. You have the layers by definition, one built on top of the other, and your choices were limited. You get Compact 1, Compact 2, Compact 3, or the full JRE. When we have modules, we need to think about what are the relationships amongst all the modules. And we've actually spent several years at this, dividing the JDK and the platform definition into modules, slicing out gratuitous connections, and coming up with an actual module graph. So rather than this onion of layers, we have a graph. So there's an edge from one module to another if it depends upon the APIs in that module. For example, the Nashorn scripting engine, it depends on the scripting API, and it in turn depends on base, but Nashorn doesn't need anything else. So the way you use this is by doing a very simple transitive closure computation. Imagine we had an application like the one I mentioned earlier. It uses JavaFX, and it uses RMI, and it uses Nashorn. Well, to figure out what other modules we're going to have, we do the transitive closure in this graph, which itself, technically speaking, is the transitive reduction of the module graph. And we see that we need TLS and logging and the scripting API, and of course the base module, because you always need the base module. Given that, we don't need anything else. It all just falls away. So for this hypothetical application, these are the only modules that you need, and the size is you only need to burn the memory to accommodate these actual modules. So that's an improvement. Now, when we deliver this modularized JDK, and we have this working in a prototype, we deliver it as a collection of files in a format that we've creatively named JMod for Java module. JMod is, at the moment, the format is based on zip files, but they're not jar files. We couldn't use the jar format as is because the jar format has no way to include native code in a sensible way. And of course, many of the modules in the JDK include not just a pile of Java code, but also one or two or some number of shared objects or DLLs, depending on your platform, as well as other stuff like configuration files and ancillary resources. So the JMod format, in the prototype it's zip. In the end it might turn out to be something else, but zip was convenient for the usual reasons that zip is convenient. So we build the JDK, we get a set of modules out, a set of JMod files. Then we have the problem of, well, how do we take some subset of those and create a custom JRE image that contains just those modules? That's our goal, is to get something that looks like a JRE. It's got a bin directory with a Java command and a lib directory with all the rest of the stuff underneath it. So basically, we want a tool that can transform binary code in one form into binary code in another form. We need a tool that many other programming platforms have, but Java has never had until now. What should we call it? Any suggestions? Can't hear you. It's been a long day, I know. Okay, what do you do when you write it? When you write a C program, you run CC or GCC, and then you run the what? The linker. Excellent. Thank you very much. And since this is Java, we put a J in front of it, and we call it JLink. So we have this tool is also in the prototype. JLink will take a bunch of JMod files. You tell it which modules you want, and it will produce a custom JRE image at the end. Let's look at a couple of example command lines. So here, JLink, we tell it the mods we want are JavaFX, RMI, Nashorn, and stick it in a directory named whatever $JRE expands into. You do that, and then you can run your custom runtime, give your app jar file, whatever else goes in your class path, and you're off to the races. Now, if you're going to write an application for this kind of target, when you compile it, it might be handy to have the compiler know what modules are going to be available. So we've extended Java-C to understand this mods option. So you can tell Java-C, oh, by the way, I'm compiling for this limited target. It just has the transitive closure of these 3 modules in it, so please limit my source code to what it can, what types are visible to it. And so if you do this and your Java source code happens to reference Corba, you will get a compile time error. Of course, some would say you should always get a compile time error when you reference Corba, but that's beside the point. And also as a convenience, it'd be nice if you have a full JRE, for debugging purposes, not to have to go generate your custom one all the time. You could have a full JRE and tell it, oh, at startup, please configure yourself so, as if you had only been built with this limited set of modules. So we have that ability too. So this is an important concept. To keep the whole development and debugging experience sane, we want fidelity across all of these phases. So compile time, link time, and runtime, we want to be able to achieve fidelity in terms of exactly the set of modules that are visible and accessible. All right, let's talk about performance. So historically in Java, performance is something that we've improved only at runtime through just-in-time compilation. In the very, very early days of Java, it's true when we only had a slow bytecode interpreter, there were things you could do with bytecodes to make things go faster and bytecode optimize. There's this whole little cottage industry of companies with bytecode optimizers. There are people who still use bytecode optimizers, but in this day and age, they basically mean nothing and they're just a waste of time. So we've developed great technology over the last 15 years to do just-in-time compilation really pretty well. But the fact that you're doing it at runtime, along with the running program using all the same processor and memory resources, it just fundamentally limits what you can do. And there are some very interesting whole program optimization techniques that could be practical in an earlier phase. And well, guess what? We just introduced an earlier phase. So what can we do with that? One example, it's not quite a whole program optimization, is just fast class lookup. Today, a modern Java virtual machine to get performance pulls all kinds of tricks in order to interpret that long sequence of jar files on the class path and make stuff go fast. But it's just inherently difficult. For one thing, it's a class path. It's linear search, and it's not uncommon to hear people having problems with this. You think about it. If you have a large application with a class path, and we've seen applications with dozens, if not hundreds, of jar files on a class path. If you go and look for, you try to load a class that doesn't exist, that requires the VM to open every single one. And each one of those is a zip file, which, by the way, is not a very efficient format for fast lookup. And you can do your best to make that go fast, but fundamentally you're limited by this linear search and by the zip format. So that's kind of a no-brainer. If we have this linking step where we can look at the whole system, we can build, say, a really fast B tree that looks up all the classes from just one place instead of doing linear search. Aggressive inlining. So every modern JIT does some amount of inlining, but there are kinds of inlining you can do at link time if you have a chance to do a little more analysis. One thing, for example, is inlining lambdas. So at runtime, you can't just indiscriminately inline all lambdas because you'll probably face a code explosion problem. At link time, we could inline lambdas because we have more time to do the analysis that we need to do to avoid unnecessary code explosion. Here's a big one: ahead of time compilation. Doing AOT now with Java is pretty tough, and again, part of this comes down to the class path. If you try to do ahead of time compilation, that is compiling native code, compiling Java code to native code, at link time essentially, well before runtime, you need some way to validate that the class path that you had at link time is exactly the same as the class path you're going to get at runtime. And that can be done with creative use of hashes and timestamps and all kinds of groveling over the file system, but it's kind of brittle. Jvm Specific Memory images. The hotspot VM has a technology in it called class data sharing that you might have heard of. We use that to improve startup time for every application. The idea of class data sharing is to load up the first several hundred, whatever classes that are used by most applications. It's a fixed list, but this works pretty well. To load those up when we install the JRE, load them into memory, build all of Hotspot's internal data structures, and then save that to disk. And then the next time the VM starts up, we just memory map that file in, and there's a substantial savings because the VM doesn't have to go interpret the bytecodes, the class files all over again and reconstruct all of these data structures. So wouldn't it be nice if we could also do that for these custom images? And finally, if you want to get really aggressive, you could do static analysis to remove unused fields, methods, and classes. Today, this is pretty tough. So how do we do this? Well, the answer is kind of obvious. We generalize the linker, right? Not only can it be a thing that takes JMods that comprise the JDK and build a custom image, it can be a tool to which we can feed application classes, whether they're in jar files or just loose class files. And we can produce things out the back end other than a JRE image that runs this one particular application. We can produce a JVM image, the memory map thing. We could produce a fat binary, one executable that contains the VM and all the class data and everything, and is one file that you can go install, and people might not even know it's Java. Won't scare them away. Since the linker is this general transformer of code to code, we could have a backend on the linker that generates a fat jar file, because sometimes that's a convenient deployment target. And we can also use JLink to construct JMod files from class files or whatever the input is. And in our prototype today, this is actually how the build creates JMods. We generate the usual build classes directory that's got every class in the entire JDK in it, and then we run JLink to create the JMods that are actually delivered. Some more command line examples. So here we're using JLink to take the combination of modules for the platform and app.jar, or whatever other jar files, create a custom JRE. And once you've done that, you've got one binary in the JRE's bin directory that corresponds to your app. You run it, and you've got your app in the VM. Start it up. We can create a custom VM image and run that real fast. So we intend for the linker not just to be a command line tool, but there will also be a supported API for it. And there will also be a plugin API. It seems to make sense to have a plugin API for the linker. So basically, you could have all of these different kinds of optimizers be defined as plugins. Plug them into the linker, and also a plugin API for the back end, so you can output different kinds of images when you're done. There's no gain without some pain. To make all this work, we need to make some seemingly dramatic changes. Our old friends rt.jar and tools.jar, how many people know what these files are? How many people have made direct reference to these files in your Java code? Okay, sorry. They're going away. So these files, they're artifacts of the way the JDK was implemented. They've existed since the 1.2 release. They were never meant to be something that user code would rely upon. But of course, since it's all fairly transparent, people have written code that does rely upon them. There's no way we can achieve our performance goals while retaining this format for storing class files. So we're not going to. They're going to go away. Stuff is going to break. Another thing that's going to change is the structure of the JDK and of the JRE. Right now, if you look at a JDK, at least from Oracle or one based on OpenJDK source code, you'll see there's the JDK, and inside there's a directory called JRE, and it's got its own lib directory, and it's all kind of confusing. I mean, that particular nesting is something that was done in the 1.2 release, was meant to be temporary, and now, how many years later, we still haven't fixed it. Well, we're going to fix that too. The structure of the JRE and the JDK will be identical, since, well, the JDK is just a JRE with a few more tools modules added to it. We'll have a bin directory, we'll have a directory for user editable configuration files. We will separate those out from things that users are never supposed to edit. Extensions, an include directory, and a lib directory that has the actual guts of the implementation. .sos or DLLs and modules in some format, TBD. But whatever it is, it will be pretty highly optimized. Okay, security. We all know Java security has been in the news the last couple of years. It's been pretty painful, but in general, I think the story is much better now than it was a couple of years ago. What does modularity have to do with security, you might ask? Well, if you look at the packages that you might find in rt.jar, you'll see package names that start with different prefixes. These are the packages that are in the base module in the Jigsaw prototype. Many of these packages are not part of the Java SE standard as defined in the JCP. Quite a lot of them are strictly internal to the JDK. A very popular one is in the sunmisc package. There's a class called unsafe. How many people have written code that uses unsafe? Okay, I'm sorry. So unsafe, if you don't know, is this magical class that is deeply in bed with a virtual machine. It allows you to write Java code that it can peek and poke and do memory fences and CAS and all this other fancy stuff. It's pretty dangerous business. So any package whose name begins with Java or JavaX is by definition part of the standard, and every compatible implementation has to implement those completely. Other things are not part of the standard, and with rare exception, they're not meant to be used outside of the implementation itself. In particular, all of this sun dot stuff. Sunmisc, sunreflect, sunutil. These are all meant to be internal to the implementation. The problem from the very beginning has been that there has been no way to keep them internal to the implementation. If you look at the definition of the Java programming language, there are only a few ways to constrain access to something. You can declare something to be private. You can declare something to be protected, which limits you to the inheritance hierarchy, or something's public. So we have all these implementation packages with implementation-specific classes in them. They need to be accessed by the implementations of the standard packages that people are actually supposed to use. The only way we can arrange that is to make all of these internal types public. And that's why people have been able to go and use them. As long as you're not writing code that is going to run as an applet or in some other sort of security managed environment, you can just go and do that. So we've developed conventions over the years using sun dot or something dot internal dot as a gentle hint that this is internal, you shouldn't use that. You might ask, well, what do you do in the case of, say, an applet? You really don't want an applet to go use sunmisc unsafe to peek and poke at random bits of memory. The way we do that is, well, it's kind of a hack. In the security manager class, there's a method called check package access. How many people have written code that uses check package access? Didn't think so. So check package access is invoked when you want to ask the question, is this class in this package allowed to access this other class in that other package? And in the implementation, we have a list of basically all these sun dot classes and a few others that are only supposed to be accessed by the JDK implementation code. Check package access is specified as part of the Security Manager API. There is, and one thing that is not specified, but this happens, and this is done by every Java virtual machine, is the virtual machine, when it is first doing constant pool resolution to link one class up to another, the virtual machine does an upcall into Java, if there's a security manager, does an upcall to invoke this method on the security manager to ask it, should this class in this package be able to access that other class in that other package? It's fairly expensive, but it works. So that check in the VM is only done in a small number of places and was easy to validate. The problem with something like this is there are a bunch of other places where the same check needs to be made. In particular, in all of the reflective APIs that are in the platform. And sadly, we have more than one of them. We have core reflection in Java Lang Reflect. We also have now the method handles, part of the invoke dynamic work that was done in JSR 292 and Java 7. And there are various other reflective facilities. So basically, every one of these reflective APIs, their implementations have to invoke check package access correctly and always. And if someone working on one of those implementations forgets, well, nothing bad happens anytime soon. There's no test that fails. There's no crash that happens. What does happen is 5 or 8 or 10 years later, you get a security vulnerability with a CVSS score of 10, and that's no fun for anybody. So check package access is basically just really brittle and error prone. Well, gee, we have modules, right? To modularize the platform, we had to understand the precise relationships amongst all the modules. Let's use those modules also as the basis of encapsulation. Let's draw a boundary around each module. Let's arrange things so that a module can only access the modules upon which it depends, both directly and indirectly. And a module can also declare, if it's an internal module, it also can declare, well, this module is only accessible by these 3 guys I trust over here, and no one else, no matter what happens. So we're doing that also in the Jigsaw project. A side benefit of doing this is we also improve the maintainability of this large body of code, because we know that, well, Nashorn will never depend upon XML digital signatures. Not that anybody would actually think that would ever happen, but by using encapsulation at this new level, at the module level, you can look at a module and it's easier to reason about it because you can tell very easily exactly what APIs are accessible to it. You don't need to worry about random code going into random places. There's no gain without pain. The Sun star packages, any package with the name internal in it, these will all go away. So if you've written code against Sun MISC or Sun this or Sun that or Sun something else, now would be an excellent time to start thinking about how to revise that. In JDK, we actually introduced a tool called JDEPS. You can run the JDEPS tool and give it a set of jar files, and it will analyze those and look for static references to classes, and it will flag any use of a known internal API. So that's one way to figure this out. Let's see. That was about that. So again, the motivations: scalability, performance, security. That's why we're doing this. Yeah, I work for Oracle. Okay, we've got some time for questions. Yes, sir. When this is coming? Oh, it's going to be an 8. No, sorry. I'm typing as fast as I can. So we would very much like to get this done in 9. I'm not going to say that it will be in 9 because I know better than to make that kind of promise. And because just also generally in JDK releases, excuse me, we're trying to move to a mode of operation, as George and I were discussing this morning, where we release on a 2-year cadence. If something's ready, then it goes in. If something is not ready, then it waits for the next train. But we've got quite a number of people working on this right now. I hope to file the JSR for it fairly soon, so you'll be hearing more and more as that process gets started. Any other questions? Could we turn the house lights up? It's hard to see people in this weird blue light. Yeah. Mm-hmm. I didn't mention anything about versioning. That is a completely true statement. So let me give you a version of my thoughts on versioning. Versioning is really hard. Our earlier work on Jigsaw, we had a somewhat different set of requirements. We were trying to solve the sort of general versioning problem. We were not trying to solve the multiple versions of one library in one process problem in a very general way. It turns out, at least from data we've seen, very few people actually need to do that. So our thinking on versioning is it's definitely important. You got to do it. It's good for modules to have versions. It's good for modules, a module dependence to have a version, so that you can tell that this module needs, version 1.2 of that other module, and 1.3 is okay also, but I don't want 1.4 because I know it's broken. Our view on versioning is that how do I put this? It's important to do, it's important to support. You need to be able to detect version conflicts. You don't need to be able to support arbitrary mixtures of different versions of the same thing in the same process, with one exception. I mean, certainly for the cases I've discussed here today, creating a custom JRE, creating a JRE that has an application built into it, it would just be a bug if you needed 2 different versions of the same thing. And the way these tools work is if they see multiple versions of something, it's just an error. You need to go fix your build so that the tools only see one version of each candidate module. Where versioning gets more interesting is in very sophisticated applications that do dynamic loading and unloading. And the typical example of that is a servlet container or an EE app server or an IDE, right? But these are fairly unusual kinds of applications. So that is a case that we want to support. In cases like that, you do need to be prepared to have multiple versions of a library, a module of the same name running in the system. But you don't need to do the full general purpose solution that some systems have achieved for that. So just to drill into a little bit of an example, you might have an app server where the app server code itself needs to parse XML, and that code has been bound to version 1.2.3 of Xerxes or whatever. But then a web application is deployed into this app server, and it wants version 2.3.4 of Xerxes. And these aren't things you don't want objects from one of those to meet objects or another, because then stuff will blow up. So we're exploring a way to compose the module graphs in the system so that if you looked at everything, you would see, oh yes, there are 2 copies of Xerxes. But it wouldn't be the case that the application itself could depend on 2 different versions of Xerxes. It depends on the one that it needs, and the app server continues to depend on the one that it needs. And when the application is undeployed, then that version of Xerxes goes away as well. Another aspect of versioning is the whole integration with other tools, right? We have no intent of competing with Maven or Gradle or Ivy or any of these other things. They already have tackled a big part of the versioning problem in terms of having ways to deal with dependency conflicts and downloading stuff and all of that. So we intend to rely on them and figure out pretty much as simple a way as we can figure out of relating the version that goes on a module to the versions that you find in POMs and in Maven Central and all of that. Way over there. Is there something in Jigsaw that limits other people's code to use your code? Yes, at least if all the code is in modules. So this is one of the things that's one of the features that's driven by our experience of modularizing the JDK is there are some modules that really are only ever used by the implementation itself, and we don't want anyone else to be able to access those. SunMISC is the prototypical example. So in the way that a module is defined, and we have a little DSL for it, a module definition can say, it says the name of the module, the names of other modules upon which it depends, and it can also list names of the modules that are permitted to depend upon it. So if there's a permits list, and another module tries to depend on it, and that module's name is not in that list, then access is forbidden in the same way that access is forbidden on all the other encapsulation boundaries. So yes, you can do that. If you're mixing legacy jar files with modules, then there's not really any way to express that. Although code in a jar file would also not be able to access code inside a module that has a permits list. Somebody way over here on the edge. Okay, let me see if I can repeat the question. Is there any benefit to combining all of your application code into one large file?
Okay, imagine that I would like to have...
Oh wait, here comes a microphone. Thank you very much.
Thank you. So question is, I would like to use linker to produce a big file with full package of GRE and my application.
Right.
And still I would like to benefit from the performance features that you have just explained.
Mm-hmm.
So is it possible, or there is some correlation? So you need either to sacrifice performance or benefit from packaging everything in one thing?
So there's no reason why you couldn't take the optimized JRE that's produced by JLink and package that in one file and ship it, if that's what you're asking.
Yeah, that's correct. But
Yeah.
if it will reload libraries, when
Why would it reload libraries?
Okay, if there is no reason, I accept this.
I mean, it should have all the libraries it needs right in it, because it's supposed to be a self-contained image.
Okay, fine.
Okay? Did you have a second question? That was it.
No, it's already dropped.
Okay. Anybody else? Yes, sir. Right, so the question is, will there be something like C#, the internal modifier? So we've considered that. Basically, I think the equivalent would be introducing an internal or a module access modifier into Java so that you could write, module and then some class, or module and then some field, and the visibility and accessibility of that element would be to the current module. It would be broader than protected or private, not as universal as public, but just within this particular module. We considered that in the very early days of Jigsaw. This is also an option that's been considered by earlier efforts to add a module system to the platform. And our conclusion pretty quickly was that becomes pretty hard to use pretty quickly, basically. For one thing, it makes modularizing an existing code base difficult. If you wanted to take all of the classes in the base module and now define the base module, you'd have to go through the entire thing and sprinkle this new keyword everywhere. Whereas with the design we wound up at, we actually don't need to modify the classes in the base module at all. The compiled form of class, in the compiled form of class, there's no indication of what module it's in. What module it's in is a consequence of how it's packaged and how the module metadata is related to it. That's a much more flexible kind of model. Another thing that enables is we have a very simple design in mind where we can create a jar file that can be treated as a module because it has proper module metadata in it. But if you also need to deliver a jar file in the normal format for use on a normal class path, you can take that very same jar file. Okay, now I have two. What was I saying? Right, modular jar files. So another advantage of having the metadata about a module, the definition of it be separate from the classes that are in the module, is we can define a modular jar file format. It works just like a jar file if you stick it on a class path, but you can also stick it on a module path, and it will behave as a module and be seen as a module. So you don't have to use a JMod all the time if you don't have any native code or other data. Any other questions? Yep. Is it possible to query a JRE image for the modules that are in it? Absolutely. We have a couple of -x options in our prototype. You can say -x list modules, and it will print you a nice list of all the modules that are in the JRE. Yeah.
Thank you. I was wondering whether it would be possible to analyze what the custom images or modules were composed of originally.
If you're looking at an optimized image, probably not. All bets are off. To do a good job of optimization, we need to reserve the right to change everything, right? So what's in there will be the code in some form, but its structure might not bear any apparent relationship to what you started with. That's just in the nature of optimization. Any other questions? Yeah, in the back. Well, it's solved it for some definition of solved. Not yet, but I hope they'll help out. We have talked with the Gradle guys, and I think we're reasonably aligned with them. But yeah, as time goes on, we'll be reaching out to all the maintainers of major tools to suggest, and maybe in some cases we'll help upgrade things to make the whole module story work. Any other questions? Yeah. I'm sorry, I can't hear a thing. I feel like a talk show host.
Thank you. My question is that, for example, if my application is using like an external jar file, which in turn uses the modules that I'm not packaging my JDK with, or my targeted JDK is not packaged with, does the JLinker throw a build error or something? Does it introspect the external jar files?
There's no magic here. The linker will not try to introspect and figure out, what things you might need. If you're linking up an application, and it depends on some jar file that you didn't give the linker, then, well, the link phase might complete, but at runtime something is going to go boom, and there's really no way around that. No, one way around that is to package everything as modules, but we don't expect that every jar file in the world overnight is going to be converted into a proper module as soon as 9 ships or whatever this release is in. That'll take a long time. Anybody else?
Just maybe a stupid question, but do you think that this module format is some kind of new jar, so you're like replacing all the jars in the future?
Is this module format some kind of new jar? Are we going to replace jar files? The jar file format is like this accident, right? It was never meant to be both the packaging format for Java code and an execution format for Java code, and it's not very good at either one of those things. But there were more important problems to solve in 1996, and here we are. So jar files will be an essential part of Java until, I don't know, the death of the universe, until Java's done. Jar files will always be supported. We hope and expect that people will be interested in modularizing their own code for the same reasons that we're interested in modularizing the JDK. So we'd like to make these facilities available, and over time, we may see many people using JMods rather than jars, or maybe JMods in addition to jars, who knows. But it's kind of like when generics were added in 5. Did everybody overnight convert everything to use generics? No, there's still large bodies of code that haven't been converted to generics. There are bodies of code that will never be converted to generics, and that's fine. It's part of one of the complexities of a widely used software platform is it sort of wears its history on its sleeve, right? Anything that was in there at some particular point, unless it was just a total mistake, is probably going to be there at every later point. And that's just the way it is, because you don't want to break existing code unless there's a really good reason.
Also, another small thing, like you said that you're able to form a binary, like one of the options was to form one all-in-one block.
Mm-hmm.
Will that be available so that, for example, you're on Linux and you're saying, okay, I want the exe block, can you do that?
Oh, if you're running the linker on a Linux box, can you cross-link and magically create a Windows executable? That's a pretty tall order. In theory, sure. Are we promising to deliver that? I tend to doubt it. Yeah, one could do that, but it's hard. It's not clear that it's worth the effort. If you don't have a Windows machine, then go spin up Windows in VirtualBox and do it that way. Okay, I think I'm out of time. Thanks very much.
Thank you very much. So if you have any more questions to either Mark or the rest of the JDK team that's around here tonight, there will be a BOF at 7 o'clock down in the C1 room. And now the party starts off in the exhibition area